To introduce this next section, I'm going to play part of a video in which a couple of people are talking about bicycling and the gears on a bicycle and how those work.
Hey Daisy, let's take a right.
Okay. Oh no, it's a hill!
This is really steep. Something I've always wanted to try is to ride up the biggest, gnarliest, steepest hill in town on my bike.
The steepest hill in the city. Use your gears, Nate!
I can't change gears, I only have one. I was just on a single speed.
I surpassed Nate.
This is so much effort.
He only had one gear. Not that much effort for me.
Daisy, with the multiple gears on her bike, changed to the lower gear, which made it easier for her to pedal.
I can go into a really low gear that can help me climb up the hill. Come on, Nate!
Oh, see you later, Daisy.
Kinda crazy. Aw, so Nate, your bike only has one gear.
Yeah, it goes from a pretty big gear in front to a pretty small gear in back. So when you go from a big gear to a small gear, it's really hard to pedal.
Okay, I want to stop here and just talk about what's going on with the gears. So the big gear here is connected by a chain to the small gear. So remember the outside edge, how fast it's traveling on the outside edge is its linear velocity. How fast it's traveling on the outside edge is the linear velocity. So if these two gears are connected by a chain, the chain is moving at a constant speed, which means the linear velocity of the two gears is the same. So that on the outside edge they are going the same speed. Now you might say, wait a minute, they're not going the same speed. Well, they are not going the same rotational speed because the big gear is rotating more slowly because it's bigger on the outside, whereas the little gear is having to rotate a lot faster to keep up with the speed of the big gear. So the linear velocity is the same, but their angular velocities are different. Now, the angular velocity of the pedal, since it is attached to the big gear, is the same as the angular velocity of the gear, and the angular velocity of the little gear, since it's attached to the tire, is the same as the tire. So the tire is rotating at the same speed as the little gear, although the linear velocity of the tire is certainly different because the radius of the tire is much bigger. So it is the tire is actually rotating much faster than in a linear sense than the outside edge of the gear is. So let's just we can spend a little more time looking at this and what happens with the gears.
Pedal. But every time you turn the crank around, the back wheel goes around lots of times.
Okay, I'm just gonna turn it once, okay?
About 3 times. Great for speed, not so good for going up steep hills. Oh man.
Now we have my bike up.
On Daisy's bike, there are 3 chain rings in the front and 7 cogs in the back. If you have a bike with multiple gears, you can choose a different gear for if you're going up a hill, across flat ground, or going down a hill. Now the bigger the cog that the chain is on, the fewer times around the back tire goes every time we turn the pedals. Now I've got my road bike with multiple gears, like Daisy's.
We're gonna test how far Nate's bike rolls at different gears.
On the lowest gear, my bike rolled about 8 feet for 1 revolution of the pedal. So now I've changed which cog the chain is on the back wheel. I went from a really big one down to a much smaller one. Right there. On a higher gear, the bike rolled about 14 feet for 1 revolution.
Yeah.
The gear we used to go not so far would be great for going up a hill. And that was the biggest cog. Now that I've got my bike with a bunch of gears, and you've got your bike with a bunch of gears, let's go try climbing that hill again.
Let's go.
I'll just tell you that time Nate beat Daisy up the hill. So we're gonna go away from this video and go to our problem now. I know we spent significant video time looking at the a video there, but I think it was very important to be able to visualize what the bike was doing. So I ride bikes. I have a road bike. It has multiple gears, but we're just kind of looking at a simple example of a bike here. I went out though and I measured my large gear that's attached to my pedal and found its radius, and I measured one of my smaller gears in my back tire, and I measured the radius of my tire. Now I neatened up the numbers a little to make them a little nicer to work with, but they're approximately what are the actual measurements of my bike. So I have asked a question here. If the bike cyclist is pedaling at a rate of 1 revolution per second, so 1 time around with the pedals, so starting here, going all the way back down to here, that would be 1 revolution per second, how fast is the bike going in miles per hour? In other words, how fast is this tire actually going when you are pedaling at a certain rate? Now notice this says 1 revolution per second. This is a measure of angular velocity. You can see this in a car. You have what's called a tachometer in most cars, which shows the number of RPMs, which are revolutions per minute, the number of revolutions of the crankshaft and the engine of the car. So lots of things are measured in revolutions per minute, for example, and those are called RPMs. Revolutions per second then would also be a measure of angular velocity. So let's start with the things we know. This is kind of a complicated problem, so we're going to break it down into pieces. First of all, from the previous video, we know that linear velocity is equal to the radius times the angular velocity. Secondly, and we can go ahead and write that in symbols, V equals R omega. Don't call it W, please. Please call it omega. We also know that 1 revolution is equal to 2 pi or 6.28 radians. So when we say 1 revolution per second, we're actually saying 6.28 radians per second. So 1 revolution per second is equal to 6.28 radians per second. And I'm going to put that in parentheses because remember that's in unitless measure. Anything rotating around the same center is going to have the same angular velocity. So looking at the bike, the things that have the same angular velocity are things connected at the center. The pedal is connected to the large gear, so the pedal and the large gear have the same angular velocity. So pedal and the large gear. Also, if you look back at the picture of the bike, the small gear is attached to the tire, so the tire and the small gear have the same angular velocity. Now we already know one of these values. We know the angular velocity of the pedal. We know that it's 1 revolution per second or 6.2 radians per second. So we're going to put some symbols on here. We're going to say the angular velocity of the pedal, which equals the angular velocity of the large gear, is equal to 6.28 radians per second. So that's a piece of information we know. We also know that the angular velocity of the tire equals the angular velocity of the small gear, although we don't know what that is yet. The other thing we know is that anything connected at the outside edge has the same linear velocity. In other words, their outside edges are traveling at the same speed. So the large gear and the small gear have the same linear velocity. So we're going to say V for linear velocity, V of the large gear equals V of the small gear. So let's talk through basically what we're trying to do. We're starting out with, we know the angular velocity of the large gear. We know how fast it's spinning. Actually, it'd be spinning this direction. We know the radius of the large gear. Therefore, we can find its linear velocity. Once we know the linear velocity of the large gear, we can find the linear velocity of the chain, which is also the linear velocity of the small gear. Once we know the linear velocity of the small gear, since we know its radius, we can divide to find its angular velocity. Then we would know the angular velocity of the tire, and we can multiply by the radius to find its linear velocity, and then we just have to change inches per second into miles per hour. So let's start with this process. So number 1, we know the velocity of the large gear is equal to its radius, 4 inches, times its angular velocity, which is 6.28 radians per second. Now this is where the fact that radians is a unitless measure comes in handy, because now I can say that the velocity of the large gear is 4 times 6.28, which is 25.12 inches per second. It's not inches radians per second, it's just inches per second, because the radians just disappears. It doesn't have any units attached to it. So now we have this piece of information. Now I know that the velocity of the large gear is equal to the velocity of the small gear. So I can say then that 25.12 inches per second is equal to the radius of the small gear, 1.75 inches, times its angular velocity, the angular velocity of the small gear. So to find the angular velocity of the small gear, I have to divide both sides of the equation by 1.75 inches. Notice the inches, well actually that whole thing divides out, but over here the inches cancel and I end up with 25.12 divided by 1.75 per second. In other words, radians per second, because remember radians disappeared before, they sort of reappear now as this unitless measure. So the angular velocity, okay, which I have over here, is equal to this value. 25.12 divided by 1.75 is 14.35 radians per second. Technically, you can just write it as nothing per second, just per second, but I think it's easier to put the radians in there. It makes it a little more clear. Now, I want to know so now I know the angular velocity of the small gear. Well, I know the angular velocity of the small gear equals the angular velocity of the tire. So now that I know that that is 14.35 radians per second, now I can find the linear velocity of the tire. So I'll go up here and start up another thing. So the linear velocity of the tire is the radius of the tire, 14 inches, times 14.35 radians per second. So now we're going to end up with inches per second again. I can kind of scoot this over so it's a little easier to see. So the linear velocity of the tire is 14 times 14.35, which is 200.96 inches per second. But inches per second is not a good way to think about traveling on a bike, is how many inches per second you travel. We'd rather have it in miles per hour, or if you're one of our international students, you'd probably a lot prefer kilometers per hour, but we're going to do miles per hour because that's what I know better. So we are going to use what's called factor label method or dimensional analysis. We're going to change our units. So I'm going to start out with 200.96 inches per second, and I want to change it to miles per hour. So I'm going to start with the inches and change it to miles. I don't know how many inches in a mile, but I know that there are 12 inches in 1 foot. So basically when I multiply 1 by 1 foot over 12 inches, I'm multiplying by a funny form of 1. Okay, this is a form of 1, so I haven't changed the number. But what's nice is my inches cancel out, now I'm in feet per second. Then I know that there are 5,280 feet in 1 mile. So now my feet cancel out and now I'm in miles per second. I want to get into miles per hour, so I need to know how many seconds are in an hour. Well, there's 60 seconds in a minute and 60 minutes in an hour, so altogether there's 60 times 60, or 3,600 seconds in an hour. I could have done that in 2 separate steps, but I was running out of room. So now seconds, my units, seconds cancel out, so I'm left with my units of miles per hour. I just have to multiply all the numbers in the numerator together. So when you multiply fractions, just for those who've become way too calculator dependent, you're going to multiply all the numbers in the numerator and then divide by the product of all the numbers in the denominator, which are 12 times 5,280, and you end up with a grand total here, 11.41 miles per hour, which is pretty reasonable. That's actually a pretty leisurely pace for biking. If you're a road biker anyway, that I'm not a super athlete, but I can road bike about 13 miles per hour without much trouble, and even faster if I'm on a smooth road or going downhill. I can get up to 16, 17 down a hill, maybe even up to 20, which is really fun. But of course, going uphill, it's much slower than that. It's a steep hill, you're down to 5 or 6 miles an hour. But anyway, that is how you can use the relationship between linear velocity and angular velocity along with radian measure of angle to do basically an engineering task. If you are building a bike, you need to know how big do the gears have to be in relationship to the tire so that you can apply a reasonable amount of force and get the bike to go to the speed you want. And if you are dealing with high performance biking, you would have to really know about the gear ratios and so forth, because somebody like Mr. Hutchison, who biked up Pikes Peak, which is a mountain in Colorado, he did that. Wow, he really had to know how to use his gears well to get up that mountain. So this is a practical application of angles and radians. Now on your homework, you're going to have the opportunity to do a similar problem with just different numbers. See if you can work through the problem without staring at your notes the whole time. See if you can reason your way through it. I'd be really proud of you, and you'll learn a lot more if you try to do it that way.